Okay, so in this lesson, we are going to put into play some of the things we learned about the calculator skills. And so again, if you're using the TI, which is what I'm going to use to show you this, all of the things that we just talked about in our last lesson will come into play. If you're using Desmos, then again, much easier than with the TI. But this is just real world examples of quadratics. And so this first one you may have heard before. It says the path of a baseball is given by the function, and then it gives you a quadratic equation here, where f of x is the height of the baseball. So y, f of x is y, and that's representing the height of the baseball, and it's in feet. And x is the distance from home plate in feet. So x is our distance, also in feet. And it doesn't give us much to go on here, but you have to assume that if the baseball is leaving home plate, then it's probably being hit by a batter. We'll tell more after we put this function in and find the domain and range of the function, whether it's the catcher throwing the ball back or if it's the batter, but more than likely the batter. So anyway, we're going to enter the function into the calculator. So here it is. And so they want us to sketch this. Well, if I use a normal Zoom 6 window, like we talked about last time, this looks like a line. And I know that it is not a line because it's an x squared, which means we've got a parabola. And it looks nothing like a parabola. So we know that we need to see a whole lot more going in the direction up and to the right. Because in this situation, negative numbers are really not going to be important to us. We can't hit the ball in a negative, well, I guess we could if we fouled the ball off or something, but assuming the ball went forward in this path, then we're not concerned about this negative distance over here, the negative x. And the ball is going up in the air, so we're not too concerned about negative y's either. So I'm going to change my window up a little bit. I'm going to get rid of the negative, well, I'm not going to get rid of it. So I want to still see the x-axis and the y-axis. So I'm going to use -1 for the x-men, -1 for the y-men. Now, like we said, we need to see a lot further on how far that ball went. And so x is how far the ball goes. And if this thing is hit by a batter, it could go 350, 400 feet if it's a good batter. So I'm going to start with 350. I'm going to change this to maybe by 25. And how high it goes just depends on how they hit it. We'll say 200. And again, I'm going to go by 25. So let's just see what we get. All right, well, that's not too bad. So definitely it was hit by a batter and not thrown by the catcher. We probably didn't need quite so much height, so if I want to go back and change that, I could change this Y max maybe to, I don't know, 100, because it looked like it was, yes, and that looks almost perfect. Now, when you're doing these problems, whatever you use for your scale, you need to tell me what scale it is. So our domain here, we set from, let's flip back over here, -1 to 350 is our window. And our domain here relative to this graph, so we're going to do this relative to the situation. So looking at this, I just need to know how far it went from home plate, which was at 0, over here to the end of my graph. From home plate to the end of my graph. So I need to find this point right here. Well, that would be a root or a 0. So second, calculate the 0. And we want to go way over here. My cursor's up there. So I'm going to move this over a little bit closer. You'll notice on this older calculator that we're not going to get that line. We just get a little arrow. But I know I need to go further over to the right, which would be negative y values. So hit enter again, enter, and there it is, 315.471. 315.471 is where that ball hits. So that's where that parabola ended. And we noticed when the window wasn't set quite right that it really didn't start quite at 0, so probably the height of the batter, and then our graph goes up and comes back down. But our domain would be 0 less than or equal to x less than or equal to 315.471, or in our interval notation that we've been doing, this would be 0 to 315.471. Can see my graph. All right. Now the range is going to be 0 to whatever the top of this is, because like we said before, our ball's not going below the ground. So this represents the ground. We just need to go from 0 less than or equal to y less than or equal to the highest point, which would be our maximum. So second, calculate the maximum, and we're going to go left and right of this point up here at the very, very top. So I need to go to the left and to the right, hit enter. So the highest value of y is 81.125. 81.125. And if we wanted to know where this middle point was, that's what this 156 for our x value, that's what that 156 represents, right here in the middle. All right, so we go to 81.125, or 0 to 81.125 with brackets. All right, so then it asks us some questions about this graph. So once we've got a good window and we have our information, we're going to look at our questions. It says, what is the maximum height reached by the baseball? Well, the maximum height would be what we just wrote up here for our maximum value of the range. So it's 81.125 feet. And then it says, what is the horizontal distance from home plate when the ball hits the ground? Well, this is home plate. Ball goes up, it hits the ground. So we already have that answer with our domain, 315.471 feet. Okay, in our second example, we are talking about the cost, C, in number of cents per kilometer of operating a car is a function of its speed in kilometers per hour at which the car is driven. And just to give a little background, it does make a difference how fast you're driving your car as to what kind of mileage you get. If you drive it too fast, then your gas mileage goes down. If you let it sit and idle and don't go anywhere, your gas mileage is down. So there's a good speed for each car. Not all cars are exactly the same, at which it gets its best gas mileage. So just keep that in mind as we're doing this question. So we're just going to type this equation into the calculator, and it wants us to graph this one on our calculator. So this is the same window as I used for the first problem. So it's not a terrible window. We probably should keep in mind how fast we think this car could go, because remember that the cost C is our Y value, and it's in cents, and the x-axis is our speed, and it's in kilometers per hour. And so in kilometers, I'm not sure exactly how many kilometers we would travel per hour we're going, but about 60 kilometers per hour or miles per hour would be close to 100 kilometers per hour. So keeping that in mind, we're probably not going to go, probably over 150 kilometers per hour. So, on this one, when we start at 0, all I'm saying is there's not really a set place to stop out here because this graph does continue up. However, this window, this x-axis, is probably a little large. We're probably not going to go 350 kilometers per hour. So I would take it down to 150 or 200. And so when I do that, it changes my graph just a little bit. But we still can see that it never comes all the way down to the x-axis. So we've got something that looks kind of like this. And because of that, our domain, we really cannot put an end on. So our domain here is just going to be values greater than or equal to 0 kilometers per hour, or 0 to infinity. And our range, we probably should use some of our scale to determine a couple of points on here. So, we definitely need this lowest point because that does determine what our lowest range value would be. So we're going to calculate the minimum. And we get x is 50 and y is 12. So 50 and 12, that gives us a good reference on our graph. And that also lets us know that our range, again, range keeps going up just like the domain keeps going to the right. So our range would be y is greater than or equal to 12, or 12 to infinity. All right, then for our questions down below, it says, how much would you spend to drive at 150 kilometers per hour? Well, 150 is a speed, and speed is our x value. And so we can do our second, calculate the value at 150, and we get 112. So 112 cents, or $1.12. And then it says, between which two speeds must you drive in order to keep your costs at no more than 13 cents per kilometer? Well, 13 cents is a little bit above our bottom point here. So 13 cents should give us a couple of intersections. And so to put 13 cents in, which is a y value, we're going to have to go to the y equations, and we're just going to put y equals 13. There's our line, and we have our two intersection points here. So we're going to second calculate the intersection, and we're going to go left and right of each of those points. So I'm going to go to the far left first. And so we have 60, 13. Oh, I think I actually got the one on the right. This one. Is at 60, 13. And then the one on the left $40.13. So when we are traveling between 40 and 60 kilometers per hour, this vehicle will get its best gas mileage. All right, so when you're working out these problems, you want to figure out whether they're asking you something like this, where they gave us the x coordinate or the x value, and we're looking for y. And in this case, we could second calculate the value or go to our table. Or if it's like in this case, where they gave us a y value, we'll need to put that in as an equation and find the intersection. So you have to determine whether you're being given an x or a y in order to know which to do.